Today we are going to discuss the topic numerical differentiation. Suppose we have a function f. We know the derivative of the function f at the point x0 is given by this limit, that is f dash of x0 is equal to limit h tends to 0 f of x0 plus h minus f of x0 divided by h. We know f is differentiable at the point x0 if this limit exists. Now this formula can be used to generate the approximate value of f dash of x naught. That is, we are simply computing this quotient, that is f of x naught plus h minus f of x naught divided by h for small values of h. So this will approximate the derivative of f at the point of x naught. That is f dash of x naught is approximately equal to f of x naught plus h minus f of x naught divided by h for small values of h. Now that is to approximate the derivative f dash of x naught. Suppose first that x naught belongs to open AB where f belongs to C2 AB. That is f is a twice continuously differentiable function on AB. And suppose that x1 equal to x0 plus h. x1 is equal to x0 plus h. Let this be x0 and this be x1. So this is h. So x1 is equal to x0 plus h. For some h not equal to 0, that is sufficiently small to ensure that x0 belongs to the closed AB. That is, we are taking h sufficiently small such that x1 belongs to closed AB. So now we construct the first Lagrangian polynomial P01x for f determined by x0 and x1 with its error term. That is, we know the nth Lagrangian polynomial with its error term is given by, that is f of x equal to p of x, where p of x is the nth Lagrangian polynomial plus this is the error term. If we are using the points x0, x1, etc., xn, that is we are using n plus 1 points, data points, then we have the nth Lagrangian polynomial p of x with error term is this, actually f of x equal to the nth Lagrangian polynomial p of x plus this error term. So here we are constructing the first Lagrangian polynomial p01x with the error term. That is, by we are using x0 and x1 only. So we have x1 is equal to x0 plus h. So from this we get f of x is equal to, by using these two data points only, we have p01x, that is p of x plus, here we have the points x0 and x1 only. So x minus x0 into x minus x1 divided by, here is n plus 1 factorial. So here is 2 factorial into fn plus 1 zeta of x. Here we have n equal to 1, so f double dash of zeta of x. For some zeta of x between x0 and x1, that is zeta belongs to x0 comma x1. Now replacing the nth Lagrangian polynomial p of x or p01x, we have f of x naught into this. That means because we have the nth Lagrangian polynomial, the first Lagrangian polynomial is p of x equal to, we are using the points x0 and x1 only. So the Lagrangian polynomial is nothing but, we know this is x minus x1 divided by x0 minus x1 into f of x0 plus point is x1. So here we have x1, sorry, x minus x0 divided by x1 minus x0 into f of x1. So this is the first Lagrangian polynomial evaluating by using x0 and x1. So here we have x1 is nothing but x0 plus h. So here we can write x minus x0 minus h, because x0 x1 is equal to, this is x1 is x0 plus h. So x minus x0 minus h. So this is x minus x0 minus h divided by x0 minus x1 is equal to minus h, because we have x1 is equal to x0 plus h. So x0 minus x1 is equal to minus h from here. So we get this is minus h into f of x0 is here. So now here x minus x0, that is x minus x0 into f of x0 plus h, that is f of x1 is nothing but f of x0 plus h divided by x1 minus x0, which is nothing but h. So this is the first Lagrangian polynomial P01x. So here this is P01x plus this term, that is x minus x naught into x minus x1, that is x minus x naught minus h, because x1 is equal to x naught plus h, divided by 2 factorial is 2 into f double dash of zeta x for some zeta x between x naught and x1. So this is the representation of f of x with the first Lagrangian polynomial along with the error term, right? Now, actually, we need to find the derivative of f at the point x naught. That is, we need to approximate the function f, the f dash of x naught. We need to find the approximate value of f dash of x naught. So, differentiating this equation, we'll get, we have f dash of x is equal to f of x naught divided by minus h is a constant. So, f of x naught divided by minus h. Here we will get f dash of x is equal to f of x naught divided by minus h into derivative of this with respect to x, that is 1, plus f of x naught plus h divided by h is again constant. So f of x naught plus h divided by h into derivative of x minus x naught is again 1 with respect to x, that is 1. So here we get, and the derivative of this, that is derivative of this term, derivative of this term. Okay, so here we have f of x naught plus h minus f of x naught divided by h. That is actually this f of x naught plus h minus f of x naught divided by h plus dx of this. That is the derivative with respect to x of this term. Okay, derivative of this term. Now this is equal to f of x naught plus h minus f of x naught divided by h plus derivative of this is actually we have if you are multiplying this we get x minus x naught into x minus x naught, that is x minus x naught whole square plus minus h into this x minus x naught, that is minus h into x minus x naught, divided by 2 into this f double dash of zeta of x. So we are going to differentiate this term, so we have differentiating this with respect to x, that is for the derivative of first function into this, that is f double dash of zeta of x into derivative of this. So the derivative of this with respect to x is 2 into x minus x naught minus h divided by 2, right? We are differentiating this with respect to x plus this into derivative of f double dash of zeta f x. So we have this into x minus x naught into x minus x minus x naught minus h divided by 2 into derivative of f double dash of zeta of x, that is dx of f double dash of zeta of x. So now deleting the terms containing zeta of x, we get f dash of x is equal to this only, that is f of x naught plus h minus f of x naught divided by h. If you are deleting that means this only, if you are deleting the terms containing zeta of x, we get the approximate value of f dash of x is nothing but f of x naught plus h minus f of x naught divided by h. Now, one difficulty with this formula is that we have no information about the derivative of f double dash of zeta of x. That is, we have no information about dx of f double dash of zeta x. So the truncation error cannot be estimated. Okay, that is the difficulty of this formula. But when x equal to x naught, when x equal to x naught, the coefficients of dx of, that is dx of f double dash of zeta of x is equal to 0, because we have if x equal to x naught, we have f dash of x naught equal to this, that is when x equal to x naught, we have here the term x minus x naught, so this will be 0, this term will be is 0, and the remaining part is minus h by 2 into f double dash of zeta of x, and this term will be again 0, that is this entire term will be 0, because when x equal to x naught, we have the factor here x minus x naught, so this will be 0. So the term containing dx of this f double dash of zeta of x will be 0 when x equal to x naught, and the remaining part will be f dash of x naught is equal to f of x naught plus h, f of x naught plus h minus f of x naught divided by h. Here it is 0, and minus h by 2 into f double dash of zeta of x. So this will be f dash of x naught. Okay, when x equal to x naught. So we have f dash of x naught is equal to f of x naught plus h minus f of x naught divided by h minus h by 2 into f double dash of zeta for small values of h. So for small values of h, the difference quotient, that is this f of x naught minus h minus f of x naught divided by h, can be used to approximate f dash of x naught. That means f dash of x naught is approximately equal to this. F dash of x naught is approximately equal to f of x naught plus h minus f of x naught divided by h, with an error bounded by this m into modulus of h divided by 2, where m is a bound on absolute value of f double dash of x for x between x naught and x naught plus h, that is x naught and x1. Here we have minus h by 2 f double dash of zeta. So if you are approximating f dash of x naught as this, so this will be the error. So an error bound will be the modulus of this value, that is when zeta belongs to x naught and or zeta belongs to x naught comma x1, where x1 is x naught plus h. So we can approximate f dash of x naught as f of x naught plus h minus f of x naught divided by h with an error bound by m into modulus of h divided by 2, where m is actually a bound of the f double dash of zeta or f double dash of x when x belongs to x naught comma x1. So this formula is called forward difference formula if this h is greater than 0. If this h is greater than 0, this formula is called forward difference formula, and if h is less than 0, this formula is called backward difference formula. So this formula can be used to find the or to approximate the value of f dash at the point x naught. This is the pictorial representation of that numerical differentiation. Let this be the function f of x, the graph of the function y equal to f of x, and let this point be x0 and this point be x1, where x1 is equal to x0 plus h. This distance is h. So this is let this be the point f of x0 and this be the f of x1 or f of x0 plus h. So the actual slope is actually, we know the tangent line is this, so slope will be this, the slope of this tangent line, but the approximated slope will be actually, that is f dash of x naught is actually approximated by this line. Okay, because this is f of x naught plus h minus f of x naught divided by h. Now we can discuss an example. Use the forward difference formula to approximate the derivative of f of x equal to ln x at x naught equal to 1.8, at x naught equal to 1.8, using h equal to 0.1, h equal to 0.05 and h equal to 0.01, and determine the bounds for the approximation errors. So here we have actually three questions, that is we need to use the forward difference formula to approximate the value of f the derivative of f of x equal to ln x at the point x naught equal to 1.8. The first question is with the taking the h as 0.1. The second question is taking the h as 0.05, and the third one is taking h as 0.01. Okay, so first we are doing the first case. We know the forward difference formula is nothing but f of x naught plus h minus f of x naught divided by h. Here we have h equal to 0.1. In first question we have h equal to 0.1. So first we are doing this the problem with h equal to 0.1. So h equals 0.1 and here x naught is nothing but 1.8. So x1 is this, or x naught plus we have x naught plus h is equal to 1 f of 1.8 plus h minus f of x naught is f of 1.8 divided by h. So replacing the value of h, we get this is equal to f of 1.8 plus 0.1, that is 1.9, minus f of 1.8 divided by h is 0.1. So this is equal to, that is f dash of x naught, that is 1.8 is approximately equal to this, right? So this is equal to ln of 1.9, because we have f of x equal to ln of x. So ln of 1.9 minus ln of 1.8 divided by 0.1. So we have ln of 1.9. You can obtain this value from your calculator. So ln of 1.9 is this 0.641853889, and ln of 1.8 can be written as this divided by 0.1. So simplifying this, we get the value 0.54066722 as the approximated value of f dash at the point 1.8. Right, that is f dash of 1.8 is approximately equal to this. So to find the error bound, we have the error bound is nothing but modulus of this, that is modulus of h into f double dash of zeta divided by 2, where zeta belongs to x naught and x1. Here we have x naught equal to 1.8 and x1 is equal to x naught plus h. We have h equal to 0.1, so zeta belongs to 1.8 and 1.9. So 1.8 less than zeta less than 1.9. Also we have f of x equal to ln x. Therefore f dash of x is equal to 1 by x and f double dash of x is equal to minus 1 by x squared. And we have zeta lies between 1.8 and 1.9. So the error bound is nothing but modulus of h into f double dash of zeta divided by 2. But here we have mod h divided by f double dash of x is equal to minus 1 by x square. So f double dash of zeta, modulus of f double dash of zeta is nothing but 1 by zeta square. So this will be mod h divided by 2 zeta square. But here from this we have 1.8 is less than zeta. So 1 by zeta is less than 1 by 1.8. So 1 by zeta square is less than 1 by 1.8 whole square. So we have 1 by, from this we have 1 by zeta square is less than 1 by 1.8 whole square, right? So we can write this as mod h divided by 2 into zeta square is less than 0.1 divided by 2 into 1.8 whole square. So this is nothing but 0.015321. So we have the error bound as this 0.015321. When we find the value of f at the f dash at the point 1.8, that is the approximated value of f dash of 1.8 is this, with h is equal to 0.1 and with an error bound of the 0.015321. Right. Now we have to find the approximate value of the f dash at the point 1.8 by using h equals 0.5 and h equals 0.1. Also we have to find the error bound. So in a similar way you can just find that values, that is we can find the approximation and the error bounds when h equals 0.5 and h equals 0.01, right? So you will get the result will be like this. You can just verify this. We already obtained that as when h is equal to 0.1, we have f of 1.8 plus h is equal to this, and the approximate value of the derivative is this f dash of 1.8 is approximately equal to this, with error bound is this. Okay, this is we verified. We found this. Now in a similar way you can just find the approximate value of the derivative at the point 1.8 by using this h 0.05 and 0.01. Also you can just verify that these are the error terms. So the approximate value will be this when h equals 0.05, you will get this 0.54797995 as the f dash of 1.8, and the approximate value of the f dash of 1.8 when h equals 0.01, we will obtain this. You just verify. Okay, and the error term will be this. So here we have h equals 0.1, then h equals 0.05, then h equals 0.01. So when h is decreasing, that is the we are just finding the value or the derivative at the point x naught. We have x naught plus h is equal to x1. So when this h is decreasing, we know as h approaches to 0, we have x1 approaches to x naught. So that will be the when the limiting case, that is the derivative, right? So the value will be accurate when h approaches to 0. So this will be the approximate value like this. By actual evaluation, we can find f dash of x is equal to 1 by x because f of x equal to ln x, so f dash of x is equal to 1 by x. So the actual value at the point 1.8 is the f dash of 1.8 is equal to 1 by 1.8, which is equal to 0.555. Okay, but this is the actual value of the derivative of f at the point 1.8. But the approximate value when h is equal to 0.01, we have obtained that 0.5540180, and these are the approximate values when h is equal to 0.05, and this is the value when h is equal to 0.1. So the nearest value will be this when h is equal to 0.01. Now if you are taking more small values for h, we'll obtain more accurate results, right?